Good morning, children. So today we are going to discuss a new topic from our fourth chapter, which is carbon and its compounds. And today's topic is allotropes of carbon. Okay. So allotropes means, simply it means different forms. Okay. See here, allotropes are different forms of an element which have different physical appearance and properties, but their chemical properties are same. So to make you understand this, I'll tell you a simple example. According to Hindu belief, we know that God exists in different forms, like Vishnu, Brahma, Krishna, Shiva, etc. Isn't it? Okay. So they are different forms of God. Okay. Their appearance is different, but they are gods, isn't it? So similarly, allotropes are different forms of an element which have different physical appearance and physical properties. Okay. But their chemical properties will be the same. Okay. So they will be physically different, like in their melting points, boiling points, color, size, shape, density, etc. will be different. But chemically, it is a single element, right? So their chemical properties will be the same. Some elements show allotropy. The ability of an element to exist in various forms is called allotropy, and that forms are called allotropes. Hope you understood. So some of the elements show allotropy, like phosphorus, sulfur, carbon, oxygen, etc. They have allotropes. Okay. Now today in this class we are going to discuss only about the allotropes of carbon. Okay. Carbon has three allotropes. They are diamond, graphite and fullerenes. So let's learn one by one. Alright, so the first allotrope of carbon is diamond. Diamond is the world's hardest natural substance known. So we are going to learn more about diamond, its properties, its structure, etc. Okay, let's learn about the structure of diamond. Okay, see here, this is the structure of diamond. You can see in diamond, each carbon atom is bonded with 4 other carbon atoms. Can you see? See, each carbon atom, if you take each carbon, it is bonded with 4 other carbon atoms. Clear? See, for example, this one, 1, 2, 3 and 4 bonding. So making a tetrahedral structure. I'll show you what is a tetrahedral structure. Okay. So 4 carbons together they make a tetrahedral structure. So a lot of tetrahedral structures are made, isn't it? A lot of carbons are bonding in this way. So what happens? As a result, a 3D network of many carbon-carbon bond will be formed. Okay. So remember, these all carbon-carbon bond are single strong covalent bonds. Okay. Each carbon is bonded with 4 other carbon atoms. You can see again this carbon is having 4 valencies and they are connected with 4 other carbon atoms. So a 3D network of strong covalent bond will be formed. Now I will show you the tetrahedral structure. So this is the tetrahedral structure. You can see one carbon atom is bonded with 4 other carbon atoms and makes a tetrahedral structure. Hope you understood what is tetrahedral structure. So this is happening in the structure of diamond. See here, each carbon again and again and again they are making tetrahedral structures. So as a result, a 3D network of strong covalent bonds are made inside the structure of the diamond. Okay. Now we will move to the properties of diamond. We know that due to the presence of large 3D network of strong CZ bonds, strong carbon-carbon covalent bonds, diamond is very hard and diamond is having very high melting point. Okay, usually more than 4000 degrees Celsius. Their melting point is around 4000 degrees Celsius. Okay. And what about the conductivity of diamond? Diamond is a bad conductor of electricity as there are no free ions. We know that each carbon atom is bonded with 4 other carbon atoms, making no free electrons, isn't it? So therefore diamond is a bad conductor of electricity. Okay, and diamonds are generally transparent and they shine in the presence of light. We know that inside the structure of diamond there are a lot of phases, isn't it? So when light enters into the diamond, what happens? A total internal reflection will happen to the light. As a result, what will happen? The diamond will be illuminated. Okay, this diagram shows how diamond shines in the presence of light. Now we will move to graphite, the second allotrope of carbon. See here, you can see a black or grayish colored solid. Okay. Now you are very familiar with graphite. Every day in the school you are using pencils, right? Okay. So the lead of the pencil, see here, this is made with graphite. Okay. So we are going to check which property of graphite makes it suitable for making the pencil lead. Alright. So this is the structure of graphite. Okay. Now in graphite, each carbon atom is bonded with only 3 other carbon atoms by single covalent bonding, and due to the continuous bonding of each carbon with 3 other carbon atoms, they make hexagonal rings. I'll show you from the diagram. See here, let's take this carbon atom. It is connected to 3 other, 1, 2, 3, isn't it? 3 other carbon atoms. Okay, and similarly in this way, continuous formation of these type of bonding, and they make a hexagonal arrays. See here, this is an hexagonal array. See, a lot of hexagonal arrays you can see in the structure of graphite. Okay, and again these hexagonal arrays are arranged as layers. See here, one layer. This is a second layer of hexagonal arrays, and many more layers will be there in the structure of graphite. And these layers are held by a weak intermolecular force of attraction. Okay, you know what is intramolecular force of attraction and intermolecular force of attraction, right? See, this bonding is intramolecular force of attraction, which is very strong. Okay, and what about this one? We discussed that in graphite a lot of layers are there. Each layer is connected with the next layer by an intermolecular force of attraction, which is called van der Waals force of attraction. Van der Waals force of attraction. Okay, that is very weak. So what happens? This layers can slip over one another. Are you getting? So this layers can slip over one another as a result of the weak van der Waals force of attraction. Okay, all right. And also in graphite, each carbon atom is bonded only with 3 other carbon, so making the 4th electron free to move. So the 4th electron is free to move in the structure. Is that clear? Okay, now let's move to the properties. So we know that it's a grayish black opaque substance. Okay, and it is very smooth and slippery to touch. Why it is smooth and slippery? Due to the weak van der Waals force of attraction between layers, or the intermolecular force of attraction is very weak between the layers. It is slippery in nature and is used as a dry lubricant. Okay, so it can be used as a dry lubricant. You know what is a lubricant? Grease, for example, is a lubricant. Oils are lubricants, isn't it? So graphite can be used in machineries as a dry lubricant. Okay, now another important use or property of graphite is it's a very good conductor of electricity. Unlike any other covalent compounds, we know that covalent compounds are non-conductors of electricity, right? but this is a very good conductor of electricity. Why it is a very good conductor of electricity? Because we know that each carbon atom in the structure of graphite is only bonded with 3 other carbon atoms, isn't it? So for each carbon, the last electron, the last valency is free there. So one electron is free. Okay. So from each carbon, one electron is free. So in graphite, millions of carbon atoms will be there. Therefore, millions of electrons will be available. Therefore, that makes graphite a very good conductor of electricity. Hope you understood it very clearly. Now the third one, it's a new term for you, which are called fullerenes. Okay, so here I have attached the structure of a fullerene. Many fullerenes are there. This is one among them. They are looking like football, isn't it? Okay, moving to discuss more about fullerenes. See here, why the name fullerenes? Let's discuss. Since this looked like the geodesic dome in US. What is geodesic dome? Geodesic domes are actually differently constructed from the conventional buildings. Okay, so there is one geodesic dome in US which is designed by the architect Buckminster Fullerene. Okay, so later on when fullerenes are discovered, their structure shows similarity with this geodesic dome. Okay, this molecule was named as fullerene. Okay, that, and it is also known as buckyballs. Buckminster Fullerene. No, so the architect name is Buckminster Fullerenes. Therefore, they are also called buckyballs. Okay, and so the first fullerene identified was with 60 carbon atoms, and it was in the shape of a football. Nowadays, many fullerenes are known. Hope it is clear to you. So today we learned about different allotropes of carbon, such as diamond, graphite and fullerene. So today's class is over. We will come again with a new topic in the coming class. Till then, take care and bye-bye. Thank you for watching.